In this video, I introduce t-distributed stochastic neighbor embedding for high-dimensional data visualization. Stochastic neighbor embedding is used to visualize high-dimensional data by giving each data point a location in a 2- or 3-dimensional map, in which Gaussian distribution describes the relation between the neighbors close to the current data point. If a neighbor has a large distance from the current data point, since the value of a Gaussian distribution becomes zero, there exists a crowding problem. t-SNE is an extended version of SNE, which generates a better visualization and avoids a crowding problem. The difference between t-SNE and SNE is that student T distribution is used to compute similarity between two low-dimensional data points. It's a Gaussian distribution when x becomes larger, its g becomes zero. However, student T distribution has a heavy tail for mu is equal 1. t-SNE uses this property to avoid crowding problem. It's impossible to preserve the high-dimensional distance in low-dimensional space, which is called crowding problem. For example, we cannot preserve the distance of points from x1 to x4 in 1D space. For example, in 2D space, from point x1 to x2 to x4 is the same in 1D space. However, the distance in 2D from point 2 to point 4 is different in 1D space. t-SNE doesn't convert the distance from high-dimensional space to low-dimensional space. Instead, it compares the probability space generated from high-dimensional space and larger probability space generated from low-dimensional space. Without mapping distance from high-dimensional to low-dimensional spaces, t-SNE doesn't find distance relation in high-dimensional and in low-dimensional spaces. Instead, converts the distance in high-dimensional space into probability through Gaussian distribution, and the distance in low-dimensional space into probability using student T distribution. t-SNE matches the probability space in high-dimensional space to a larger probability space in low-dimensional space. We use the student T distribution with 1 degree of freedom. Mu is 1. So the joint probability Qij in low-dimensional space is written as here. When Yi minus Ij in low-dimensional map is large, this term approaches inverse square law, which makes the invariant representation of joint probabilities to changes in scale of the map for map points that are far apart. The loss function C is defined by KL divergence. The gradient of KL divergence between P and student T-based joint probability distribution Q is computed by using this formulation. For more details, please check with these references. Thank you.